paper is performance modeling and analysis of an OpenStack IaaS cloud computing platform. This slide presents the outline of today's presentation, which is divided into 5 main sections. First is introduction, and second is an open human model. The third is scheme diagram, and the fourth is result, and the next one is conclusion. As cloud service become increasingly widespread, the performance of cloud computing platform has become a key consideration in system design and deployment. Cloud computing offers an on-demand, elastic, and real-time network access model that enables the sharing of computing resources across the globe. The three main service models of cloud computing are software as a service, platform as a service, and infrastructure as a service. This paper proposes a new stable open computing network model, QNM, composed of single server and multi-server queuing stations, with a focus on the IaaS architecture using the OpenStack open source cloud computing platform. The model simulates the request processing flow in a system consisting of the following components, each corresponding to a queuing station. The table outlines the characteristics of each station in the queuing network. Then I introduce the model flow. The first is user request enter the system following a poison process and are first processed by the firewall, where some requests may be filtered based on predefined criteria. And assembly requests are then forwarded to the controller for resource scheduling and validation. If the compute resources are not yet called on, the request is redirected to the admin to initiate the follow-up process. And the request then proceeds to the compute node, where the VM is actually created. And if external storage is required, the request is routed to the storage node. Finally, a success or failure message is returned to the user via the output node. And the left side is a diagram illustrating the overall flow of the queuing model, while the table on the right shows the routing probability and service request for each station. The probability from stage 1 to station 2 is 0.8, and the probability of being dropped is 0.2. Here we can spot an error in the original paper. The station 2 to station 3 is 0.3, and station 2 to station 4 is 0.8. It should be equal to 1, but the value should add up to it's 1.1. Therefore, I adjust station 2 to station 3 to 0.3, and station 2 and to station 4 is 0.7. And then the station 4 to station 5 is 0.15. Then the station 4 to station 6 is 0.85. The right side of the table shows the service rates for each station. However, the author did not specify the number of servers for station 2 and station 4. So I assigned both of them server is 3, which may lead to slight difference in the result. And next, let's take a look at the experimental result. And this slide illustrates the change in mean system time. As we can see, when the arrival rate lambda increases, the system time rises sharply. The chart on the left shows the result from the theoretical model, and the one on the right presents my simulation data. Both graphs exhibit a similar trend. This slide illustrates the change in the mean number in system. And we can observe as the arrival rate increases, the number of requests present the system also continues to rise. And the left side shows the theoretical model result, and the right side is my simulation data. And this slide presents the trend of the mean waiting time. From the graph, we can observe that as the arrival rate increases, the system's waiting time also increases significantly. And the left side is the theoretical models. And the right side is my simulation data. This slide shows the mean number of requests in the queue. And the left side is the theoretical models, and the left side is my simulation data. And here, this slide shows the utilization of the firewall station. Changes as the arrival rate increases. We can see that both the theoretical and simulation results follow a linear trend. As arrival rate reaches 2.0, the utilization approaches 0.8, meaning the firewall is becoming more heavily loaded. This slide shows the utilization of the controller. And as the arrival rate increases, we see that the utilization of the controller also increases steadily. Both the theoretical and simulation results shows that when arrival rate reaches 2, the controller's utilization is close to 0.9. This suggests that the controller is heavily loaded and is likely to become the system's bottleneck. Without additional capacity, it can cause significant delays and limit overall system performance. And this slide shows the storage utilization. And as the arrival rate increases, we observe a linear rise in utilization from both the theoretical model and my simulation data. Although it's not yet saturated, it's important to monitor this trend, especially if future workloads become more bursty or exceed expected volumes. However, resource planning can help prevent this station from becoming a bottleneck. This slide summarizes the key findings of my research and analysis. First, due to some errors in the original paper's routing probability results differ from those presented in the paper. And second, the simulation reveals that the controller is the bottleneck in the open queuing network model. In other words, its results on the main limiting factor for overall system performance. And finally, the future work. More complex arrival processes can be modeled using a compound Poisson process, or velocity traffic patterns can be simulated with the generalized potential distribution. This enhancement would make the model more representative of actual cloud traffic characteristics. And thanks for listening.
I've seen you choose the figures with the linear trend, almost linear trend. So any other performance measures, and so that not linear trend only. You have the increasing trend, linear trend, simply for all the performance measures.
Yes.
So my suggestion, maybe you need to have the other performance measures so that you can check different aspects of the system.
But the result from the papers is
Only focus on these.
yes.
Okay. So if so, not so good. If so, it is not so good. All right. That's it. Thank you. Hopefully you can find your way to better that.